Hello, I've returned back. We just completed the discussion on loads, and we talked about the LED as an example of a load. First, we said you need to have an idea of what the component looks like and its connections. Also, you have to have an idea of what the circuit drawing would be in an electrical schematic and its connections, and how it relates to the physical device. We need to know what does it actually do. What happens when you apply a voltage to this component? Well, we know the LED creates light. And there are other components that does different jobs, but you have to be specific as to what your component actually does when you apply electrical energy. And then you need to know what will be the purpose of this component in your project. The LED has many functions depending upon the application. It can be used to determine if something's on or off. It can flash during some type of activity, or you can use its optical characteristic to transmit or transmit information. If you're going to actually use this LED, then you need to look at the data sheet and get the four basic properties. Include the voltage, current, its power rating, and frequency, depending on whether you're using the DC or the AC part. Some components can only be used as DC, and some components can only be used as AC. But an LED can be used both AC and DC, depending upon its application. Now we will move to the next step, which is to create an actual circuit. And for this, you need some extra components. First, what you do is you basically lay out your component. And I'm carefully making all the necessary labels so that I can be very complete in my design. Now this LED from the data sheet, usually since the LED is a diode, you probably find something on the data sheet called a forward voltage, like forward bias. I learned from one data sheet that the forward bias of a typical green LED diode is about 1.7 volts. And if the diode is operating at this voltage, it will produce a forward current of about 10 milliamps. So this would be the electrical information that is related to the operation of this diode. What that means is that if I apply 1.7 volts across this diode, then I can expect a current of 10 milliamps. So if you can go to the market and you can find a battery that's rated at exactly 1.5, 1.7 volts, and if that battery has enough current capacity, you need to know about this word. It's called capacity. You have to know this. What is the capacity of your supply? It's a word that's used when something is being given to something else. What is its capacity, or what is it capable of doing? What can it do? Well, this power supply here can supply an average of 1.7 volts over a range of current. Once it goes over that current value, then the voltage will not remain at 1.7. It will probably begin to fall. So you would have a graph that looks something like this. As the current coming out of the power supply increases, it probably will give you a steady 1.7 volts. But as more and more current is being taken away from that power supply, eventually two things will happen. One, it will start to get hot, and number two, the voltage will begin to drop. But as long as we keep the voltage, as long as we keep the current coming out of the power supply below its capacity, then we can expect it to maintain 1.7 volts. So if you are able to find a power supply at exactly 1.7 volts, and you were to join this, perhaps I would also use a switch to this circuit, to this diode rather. And now I have a closed circuit. A current flows around the circuit if I close the switch. I can expect the circuit to produce 10 milliamps because that is the rating for the diode. It's rated at 1.7 volts at 10 milliamps. If the voltage is less, you get less current. If the voltage is more, you get more current. Now this is nice, but you probably will not be able to find a battery or a power supply that's exactly 1.7 volts. So you probably will find power supplies with values such as maybe 5 volts, maybe 3.3 volts. You might find some that are 9 volts. You might find a one-cell battery at 1.5 volts. Probably the next number would be 12 volts. And you probably find 24 volts. Now, I do not know the history behind these numbers. I know the history behind this number is a standard voltage for digital circuits. And this voltage here was the standard voltage for transistor radios. This is like a standard voltage for car batteries. The other voltages came about due to other electronic devices. And this is a standard operating voltage for PLCs in manufacturing. So these are very common power supplies that are developed by the industry. So you may have to choose one of these power supplies to operate your load circuit. Let's use 5 volts as an example. So we get our 5 volt power supply. And over here we have our LED, which only needs 1.7 volts to operate. It can probably operate more than 1.7 or maybe a less, but ideally we want to be as close to 1.7 volts as possible because this LED is very sensitive. Well, most electronic engineers know that if you join 5 volts across a component that only operates at 1.7 volts, then you're going to get a damaged component. So that's not the right thing to do. So you obviously need some way to reduce the voltage from 5 to the 1.7 that you need. Now there are many ways to do this in electronics, but the easiest and simplest way to do this would be simply to insert a resistor in series with the circuit and then calculate the right value of the resistor that will reduce the voltage so that the final voltage available for the LED will be 1.7. So using a little bit of math, and we're talking very simple math here. Math in electronics generally is a lot more complicated than this, but this is our first try, so we will stay simple. I calculated 3.3 volts, which means 3.3 volts must be subtracted from the 5 so that the remaining voltage will be 1.7 volts for the LED. So far, so good. But there's another requirement. The current must be 10 milliamps in order to maintain the operation of the current of the LED. So, since this is a single circuit, a series circuit, we know through the rules of electronics that all the current in this one loop will be the same. Therefore, it will also be 10 milliamps going through this resistor. Now we have enough information to calculate the value of the resistor that will subtract the proper voltage and maintain the proper current in the circuit. So using a little bit of math, we get approximately 333 ohms. This is called a load circuit. What makes it a circuit? Well, number one, the first thing that makes this a circuit is that it has a power supply. The second thing that makes it a circuit is that it has something called a load. The third thing that makes it a circuit is that it is a closed loop, meaning energy can come out, flow through the wires and semiconductors back to the negative. So this has a path. Once this switch is closed, then current can flow from one side to the other through the resistor, through the load, through the wire, back to the negative side. And that makes it a circuit. That's the definition of a circuit. So what is the difference between a load and a load circuit? Well, a load is just the component that you're going to operate. A load circuit provides the correct energy that's needed to operate the component. So this is the end of our discussion on load circuits. Our next discussion, we finished loads, and now we finish load circuits. Now we're going to talk about a special case called microcontroller load circuits. Thank you.